Hi everyone, this is the NumPy approach. We're at PyData San Francisco. It's Saturday, August 13th, 2016. So as I was saying before the talk started, I just wanted to let you know, I give a lot of talks at different PyData events, and usually the talks I give are very advanced talks about C Python hacking or crazy things you can do with Python. This is a departure from that. This is a novice level tutorial, design exercise in how to use NumPy. This talk was born out of some discussions I had with people who are software engineers, had a lot of experience writing code in C++, in Java, in Python, who had never before really used MATLAB or R or used NumPy, and needed some understanding, some better understanding of the approaches that we take, the vectorized approach that we take, the Fortran 90 style approach that we take when writing code in NumPy. So what I decided to do was put together a small presentation in order to show, as a design exercise, the way that somebody who really only knows pure Python would write this, and somebody who knows pure Python very well would write something, and then how somebody, a not completely naive and also not incredibly sophisticated, but a middle-of-the-road programmer familiar with NumPy, how they would write the same code, and to highlight some of the differences and some of the differences in that approach. So let's get started. So we can start real simple. If we're doing anything with vector manipulation or matrix manipulation, we could define a function called dot. And in pure Python, we might write dot like this. We're dotting a vector u and a vector v, and we just end up multiplying all the components of u and v and summing that. And you can see if we create two vectors of numbers randomly chosen from 0. And I get the result. And so another example, if I have A and B here, I can multiply these two matrices, and the result is, what you have here. And you can see everything here is written in pure Python. There's no use of any of the data science libraries that we're familiar with. Very simple code, and something that somebody who had familiarity with pure Python might use as their approach. This is the approach that I've found that people who have a lot of experience writing C++ or C use, where they expect to be able to manipulate vectors just using the built-in C arrays. And so they say, well, Python has lists, and lists are just C arrays but better, so I'll do the same kind of manipulations using those. But there's a reason we don't do that. And the most immediate reason that we don't do that is if I have A and B as these two list of lists representing matrices, and I multiply them together with my naive Python matmul, it takes 14.2 seconds to do. And if I do the same thing using NumPy, it takes 164 milliseconds. So we can see immediately that there's an order of magnitude, or even 2 orders of magnitude difference in these two approaches. And that's oftentimes our very first intuition as to there might be a better way out there. So with that said, I want to show you an example of a design exercise that I went through, writing code in a very pure, fluent Pythonic style, and then rewriting that in a NumPy style, and highlighting some of the differences. So to make this a little bit more interesting than something as synthetic as what we looked at before, we start by just considering a very simple definition of, or rather a fairly simple problem statement for a genetic algorithm. And the problem statement looks like this. We want to implement a binary genetic algorithm with fitness proportional selection, 1-point crossover, bit flip mutation. The chromosomes are going to be some structure that have either 0 or 1s. The fitness of that chromosome is the number of 1s in the chromosome. The optimal solution is then a bit string or a chromosome that has only 1 values. And we want to simulate this for various population sizes and various chromosome lengths and graph it. So that's our requirement. So let's think, how would so disparagingly, I like to call the style of Python that I'm about to write here, stick up your butt Python, because I know we've all worked with people who are really, really hardcore Python programmers, and they're very nitpicky about style and best practice and PEP 8 or Flake 8 or who knows what, and very prickly about, oh, you should use a generator here rather than something else, and they may belabor some of what we consider to be, or what we broadly call Pythonic code. They may belabor that notion more so than the rest of us who are a little bit more focused, or for whom maybe code quality doesn't matter as much as time to delivery. So what they might say is, we need to represent a random chromosome in order to do the simulation. So what we'll have is a generator expression that randomly chooses zeros and ones infinitely. So here, this random chromosome is some function that gives you a chromosome of infinite length. Because in a pure Pythonic style, why would you ever define the length of the chromosome that you need? You want to use an iterable and then use tools like islice in order to chop that up. And so in order to get the random population, what you do is you just take your infinitely large random chromosome, you slice it to the length that you want, and then you generate a population. You can see this random population is also a potentially infinite random population, because that would be, I would say, a more pure Pythonic style, where instead of fixing the size of these structures, you use tools like iter tools in order to put that functionality in the hands of the users of these functions rather than specifying them yourself. I've given a lot of talks about generators, and why this is a good approach to use is covered in those talks. It's mostly about eliminating modalities in the code and allowing some of the functionality that you want, namely choosing the size of the population or choosing the size of the chromosome, to be firmly in the hands of the person who's calling the code rather than in the hands of the person who writes the code. Additionally, there are some performance benefits, namely around memory usage, or at least around being able to control memory usage. That said, we can see this put into use. So we need to construct various populations. So for our simulation, we'll look at populations of size 5, 10, 20, and 50, and that's the size of the chromosome itself. So 5 zeros or ones, 10 zeros or ones, 20 zeros or ones, 50 zeros or ones, and we'll store this as a dictionary. That's the most reasonable Python type for us to use, where we map the length to the population. You can see each population is of size 10. So here's all of our populations. You can see the fitness of this population is somewhere in the middle. This chromosome here has very good fitness. This chromosome here has the worst possible fitness. And what we should see with our genetic algorithm is we should converge towards this kind of perfect fitness of all ones. So the next thing we might want to do is figure out what the fitness is. So the fitness of this chromosome could just be represented as just a simple average. We sum all the ones in the chromosome. Again, it's just a list of Python integers, zeros or one values, and we divide by the length. And so if I take the fitness of one of the chromosomes in my population, I get 0.6. This fitness will be tied into the probability of mating. So the fitter chromosomes have a higher probability of then going on to mate and create similarly fit chromosomes. So you can see we're trying to generate a probability from 0 to 1 of this chromosome being chosen as one of the potential pairs in a mating. And so you can see here we can calculate all the fitnesses of our population. So we want to figure out what the probabilities of the population are. Now we want to scale these. So what we'll do is here, since even though we want to figure out what the relative probability of any one chromosome being picked out of this selection, so what we'll do is we'll calculate the fitness for every chromosome, and then we'll scale that by the total fitness. And so that'll give us a scaled weighting of which is the most likely chromosome to pick based on this fitness. And you can see we're using a list comprehension for this structure. We're returning a generator expression because there's no need to materialize this data until it's actually used. And when we call this on our data, we can see here are the probabilities. These two chromosomes are more likely to mate than these two, which have lower fitness. Next, we need to figure out, so this is actually where it gets very tricky. We have to compute a weighted choice because we need to go through all of our chromosomes and with some weighting, randomly choose two of those. Unfortunately, in the Python random module, random.choice has no way to provide weightings for you. So we have to go through what is somewhat of a labored exercise that indicates to us that the authors behind the Python random module may not have considered all of the statistical uses of the random module. And so certain functions that you might expect to be available, like being able to randomly choose from a non-uniform distribution of a set of categorical values, is not available. So we end up having to write that ourselves. And we try very hard to write this in as pure a Python fashion as we can, using fancy things like list slicing and making sure that we zip things together. given that, which admittedly is a little ugly and maybe there might be a way to improve it, we can then write select, which takes a population and selects all of the mates for our population. What we do is we calculate all the probabilities, and then infinitely we just pick two chromosomes, and those are the pairs, and we yield those. So here we have another infinite iterator that gives us pairings of mates selected by their probability. And so you can see what we can do is we can use weighted choice to randomly choose which of these to pick, and you can see if we give the weighted choice as a function that takes the categories, the elements that you're choosing from, and also the probabilities here. So in this case, you can see B, D, or E are the only ones that would be chosen. A and C would never be chosen. What we can see if we call select, we can pull out one element from this population, and we can see these are the two pairs that were chosen based on their probability to mate. Once we have that, we need to implement one kind of mutation. So the mutation that we need to have here is single bit flip mutation. Our single bit flip mutation just works by randomly deciding one index and then flipping the value at that index. Now, one thing that we're going to do here is we're not going to flip it in place. We're going to do a copy so that we don't mutate the original data. We just return a new chromosome with that one bit flipped. And so here you can see we have one selection of a chromosome from our population, and then we did a random bit flip, and you can see this bit here is what got flipped. Once we do that, we need to implement crossover. So for crossover, what we'll do is we'll randomly select if it's the mother and the father this way or the father and the mother this way. We randomly select a position, and then we take the chromosome up to that position, or the mother up to that position, and append the father up to that position, or from that position onwards, or the other way around. So very simple crossover in a pure Pythonic style. And so you can see if we randomly select two mates from our population here and here, and we cross them over, this is the result of hybridizing these two chromosomes. And we get something that, in this case, happens to be more fit than one of the parents and only as fit as the other parent. Lastly, we need to have some mechanism in order to actually do the simulation. We need to be able to breed these chromosomes. So we take a list of mates, we take a mutation rate, because we're not going to mutate every chromosome, we'll only mutate according to some user-defined rate. So we'll do a little bit of trick with the choice function in the random module in order to determine whether or not a chromosome will mutate. And then what we do is we just say for each of the parents in the mates we were provided, we create the child by crossing over those two parents. We are doing this, again, in a very pure Pythonic style, so we're going to use functionality like iterable unpacking. And then we'll try to mutate that child, and we'll give that child a couple of different possibilities to mutate. So we'll allow the child to mutate one time for every bit in the chromosome. So for the chromosomes that are 20 bits in length, we'll give them 20 choices to mutate. For the ones that are 5 bits in length, we'll give it 5 choices to mutate. Now, I know some of you in the audience may be very familiar with evolutionary algorithms, with genetic programming, and I'll say, remember, this is a very, very simple application from essentially what you might find at the back of a textbook for an introductory book, just in order to make the design interesting, but without belaboring some of the domain-specific content. So here you can see we have our population. We select our mates, and so we're going to select 5 mates, and so these are the mates that are selected. These will be bred. When we breed them, this is the result of the population. So those original 5 chromosomes breed to create this new generation. Once we have that, we're done. We need to put this into some top-level simulation code, so we'll determine the number of steps that we're going to run our simulation for, the population size for each of the populations, the sizes of each of the chromosomes, so we'll look at 5, 10, 20, and 50 bits in length, and then we just need to run this in a loop, taking the previous population, breeding it, creating the new population, and so on. So we run this in a loop, we can see we create the new population for each run, then we just mate that population and append it. Now we want to collect all the information about all the populations. We want to have a snapshot in time of how that population evolves. So we don't want to throw away any old data. So what the resulting structure will look like is a dictionary keyed on the length of the chromosome with a list where the index of that list is which step in my simulation, from step 0 to step 99, by each of the different runs. So we'll actually potentially do this in multiple runs. And so when we take that and we graph it, we see something that looks like this. Now, by the way, this simulation ends up taking 2.6 seconds for populations of a size 100, for 100 steps each for our 4 chromosome sizes. And when we graph it, we get something that looks pretty reasonable. We can see this is graphing the fitness over time. So at step 0, most of the fitnesses are around 0.5, which is what we'd expect since these chromosomes were randomly generated. So there's an equal probability of having a 0 or a 1. And over time, they converge to perfect fitness. And what we can see is for the bit sizes, the smaller the bit size, the faster it converges to perfect fitness. That's what we'd expect because there's fewer areas for mutation. So these are the exact results that we'd want. You can see for the bit size of 20, it takes a fairly long time for it to converge to better fitness. So that's our exercise. And that's an approach that I would expect somebody with familiarity with Python, but no familiarity with MATLAB or R or NumPy would write this code. And they'd actually be very proud of themselves in writing this code, but there are a couple of things that are missing. Number one, and I won't say that, and I don't want to disparage the person who would design it in this fashion, but I want to point out some limitations. Number one, the use of Python lists to represent vector data is a bad idea. Python lists are strictly collection types, and they only really represent collections of data. They don't represent matrices, and they're not very good at representing vectors. One clear indication of that is in the very first example that I showed you, it was actually pretty ugly syntax to multiply those two matrices, whereas with NumPy in Python 3.5, we have our nice matmul operator, and so the syntax is at least much nicer. We can do element-wise operations in NumPy much easier than we can code lists, even using things like list comprehensions in Python. Additionally, it's not very fast. For these explicit Python loops are loops which the Python interpreter has to interpret itself. There is a lot of overhead for function calls in Python, and so having a lot of Python function calls in a tight loop doesn't give us very good performance. And this is necessary because the Python list provides us with no guarantees as to the contents of that list or the interrelations between the contents of that list. So for example, a Python list can be completely heterogeneous. You have no guarantee that it's set to a specific data type, so you can't specialize an operation being performed or being broadcasted across a list in any fashion because you have no idea what the types contained in that list are until you see them. And additionally, you have no guarantees about the interrelations between the types. Because a Python list can contain rich Py objects, those Py objects could have interrelations. So you could have some operation called on one of the Py objects in that list that then mutates another Py object in that list. So there's no way to automatically parallelize that. There's no way to reduce the complexity of what you have to compute in order to do an aggregate operation on a Python list. And that's one of the core reasons why we're going to redesign this in NumPy. The NumPy ND array is a data type that restricts us in some severe ways. Number one, it restricts us by requiring that we think in terms of machine types. Operations on Python integers are actually reasonably fast, but they aren't necessarily specialized to machine operations. Because Python integers support arbitrary precision and size, it's possible that you could have integers of some arbitrary size, what was originally called in Python 2, the long object. And there's no way for you to say specifically that an operation being performed on a Python list is only going to use specific assembly instructions because the contents are only 32-bit or 64-bit integers. NumPy requires you to think in terms of machine types. And so when you look at the D type of a NumPy array, it might say int or it might say float, but it's saying int because it's using the default size of the integer on your machine. Internally, it really is specialized to a 32-bit integer or a 16-bit integer or a 64-bit integer. Similarly, the float type is specialized to that. The reason for that is when you perform element-wise computations on a NumPy ND array, the NumPy internals want to actually perform those computations as efficiently as possible given the machine knowledge of those types. So for example, if you have 64-bit integers on a 64-bit machine, it wants to use single assembly instructions in order to add them or multiply them, rather than having to perform dispatch at that step. Additionally, one way that we can see is the pure Python approach is really one of trying to build this simulation in terms of small, completely independent elements, such as you breed one population, and that's one operation, and you call that in a loop, and that forms another operation, and creating those building blocks in that fashion. When we rebuild this with NumPy, we'll see that because NumPy is a tool for n-dimensional arrays, we have this almost a dimensionality trick where we can take what in Python would be explicit looping and then represent that in NumPy as just one more dimension on our matrix, which is then performed as a very efficient, is then performed as part of a very efficient element-wise operation. So let me show you how we do this in NumPy. And I'll repeat my disclaimer from the beginning. This is, whereas the first approach was very nitpicky Python, this approach is not very nitpicky NumPy. There's probably some areas where I could write this NumPy even better. It's not a completely naive NumPy approach, and you'll see that in one or two places where I do something that you might not have expected. So we'll start with the most basic. We want to represent the chromosome. And so, you know, NumPy gives us machine types. The bool is NumPy's representation of something that's either 0 or 1. Internally, it's probably going to represent this as whatever the machine size int is, because representing the bit flags probably isn't that efficient, since doing operations, doing element-wise operations on bit flags, I don't know that you can do that faster than you could do it on blocks of memory that's of fixed size. So you can see we're going to use parts of the NumPy random module. We'll generate the entire chromosome at once. One thing that's different here is in our Python approach, we had our building block was generate an individual value for this chromosome and then loop to create the entire chromosome. The NumPy approach is immediately removing that one layer of looping, that one layer of nesting, where our NumPy random function allows us to give it the size of what we want to generate. And all of that looping is happening internal to NumPy, where the NumPy code has certain assurances that it doesn't have to do dynamic dispatch, that it doesn't have to know too much information about, or that it doesn't have additional requirements on the information that it has to have in order to perform that computation. And so it can perform this much more efficiently. Our fitness function is just numpy.mean. It's as easy as that. And so we can calculate the fitness of our chromosome. In order to calculate our population, that's pretty easy to do. We just randomly generate, instead of using the code for randomly generating a single chromosome, we actually rewrite that same code to generate a random population. Because a random population is not generate a random chromosome in a loop and collect those. It's just generate a NumPy ND array of one greater dimension. And you can see the rows of this represent each chromosome. Sorry, the rows represent each chromosome, and the columns represent each of the bits in that chromosome. If we want to generate the probabilities, again, the code is much simpler. We just take the mean across an axis. So previously in the code, we had to do an explicit looping. Here we can just use the axis mechanisms in NumPy to perform the mean just across the rows, and then divide those with an element-wise computation by the sum of all the fitnesses. And so you can see here are all of the fitnesses of all of the chromosomes in my population of 10 chromosomes. In order to choose two mates, what we could do is we could just create NumPy arrays with the indices and do an NP choice. We could choose from those, and we could see this says pair chromosome 2 with chromosome 1. And we could do that with, let's see if we can get this off to the side. We can do that, we can pass np.choice a size parameter, so we can actually select all the mates as a single building block NumPy operation all at once. So here we have a chromosome, and we want to do something like flip a bit. We want to see what happens when we do the random mutation. Well, one thing that we could do is we could do an index operation and then just XOR it with a true value. Because as we remember, XORing with a true value has the property of making a false into a true and a true into a false. And so here you can see this chromosome had its single bit flipped at this position. And we can randomly determine what that position is. Now, one thing that we might see is that if we wanted to do that crossover, we can't add NumPy arrays in the same way that we can add Python lists. There's a reason for this. Python lists are collections, so it makes sense to be able to combine collections by using some concatenation operator, which happens to be the same as the addition operator. However, NumPy ND arrays are vectors, and it doesn't really make sense to append vectors. It's not something that we do that often. It's not a completely unusual operation, but it's not something that we do. And so you can see when I try and do the crossover in the same style that I do it in Python, it just tells me these two vectors are of the wrong shape. Plus doesn't mean append anymore. It doesn't mean concatenate anymore. It means element-wise addition. So I needed a different approach. Well, the different approach that I could do is I could create an empty ND array, and I could just use the slice assigning to assign it an empty ND array. And so you can see here, I chose the position for where the crossover occurs. I created an empty ND array, and then I just performed assignments in order to perform the crossover. Now, in order to actually do my simulation, I need to have a dictionary representing all of the populations for that simulation. I need to pick the mates, figure out how many children they have, breed them. When I breed them, I need to perform crossover and random mutation. But one interesting thing that we know is that each population is the same size as the previous population. So we can use that information in order to do another dimensionality trick where instead of having a 2D NumPy array where each row represents the chromosome and each column represents a bit in that chromosome, we could make it a 3-dimensional NumPy ND array where that additional dimension represents each stage in our simulation. So that's one more dimension that represents the simulation evolving over time. Now, one thing that we can do with NumPy is we can do some of our slicing tricks, our fancy indexing. So here you can see we can select single bits out of this. This is saying select every row, select every chromosome, and just select the bits from 3 to 6 in that chromosome. One thing that let's see, that one doesn't work. So one thing that we can then do is we could think, well, we could maybe try to sort these chromosomes on a specific axis in order to determine, what we want to determine here is we want to determine what the indices are. And so here, if we had, what we want to do is we want to take these populations and we want to figure out what are the mothers and what are the fathers, what are the two sides of that mating. What we could do to represent the crossover is as follows. We could perform this as a matrix operation. We could take all of the parents on one side and all the parents on the other side. We could determine a random index. So I wish this cell had run, but this cell just randomly determines an index for where the crossover occurs. Actually randomly determines multiple indices. We can determine all the indices at once. So what this cell does is it randomly determines where the crossover will occur for every individual chromosome. We can use that and a little bit of matrix multiplication in order to perform the crossover. And so you can see here, we're actually creating a mask which has 1s up to a certain point and 0s at the end, and 0s up to a certain point and 1s at the end. We can negate that mask in order to flip it, and we can just take element-wise all of the parents on one side, multiplied times the mask, plus all the parents on the other side, multiplied times the inverse of the mask, add them together, and as an aggregate operation, perform the mating like that. And so you can see one thing that we can do with NumPy is we can do other fancy indexing, like we can select the first, the second, and the third chromosome all at once. What we might want to do is select the number of couples. So we want to figure out how many couples we have, and here you can see I randomly generated all the couples. So this says 10 couples, 2 and 6 will mate, 1 will mate with itself, 7 and 2 will mate, 3 will mate with itself, 3 and 7 will mate. And what I can do is I can use my little trick here to randomly select what the populations look like, where the mates are, then perform my little crossover trick to cross them all over. And you can see there's no explicit looping here. In Python, we had at least 2 or 3 levels of explicit looping. In NumPy, we just use a fairly simple matrix multiplication trick and some masking tricks. What this requires is that we think in terms of matrices and we think in terms of bit operations. Now, what we need to do is we need to mutate these. And mutating them all at once is a little bit tricky. So what we'll do is if we thought there's a mutation rate of 1, and we randomly selected where that mutation would be by doing a NumPy choice with a specific size, here you could see this says mutate only the last bit, this says mutate none of these bits, and this would have mutating of the first 2 bits. The problem is this approach won't account for a bit being flipped multiple times in a row. In the previous code, I gave the chromosome 5, 10, 20, or 50 chances. Sorry, 5, 10, 15, or 20 chances in order to have a bit flip. And so some of those bits could have been flipped and then flipped back. With this approach, if I try and generate a true-false value at the same shape of the population to represent where the bit flips are, then I won't have the possibility that a bit could be flipped a certain number of times. So I have to do something a little bit more clever. What I know is that in NumPy, I can create an empty array containing all zeros. And I know I can create an index, and I can select out of that index, or I can use the assignment to assign into that index using a specific value. So here, assigning with a NumPy array allows me to assign the value 1 to all the positions that are specified here. So this puts a 1 into all these positions. So what I could do is I could generate a zeros array of 2 dimension, and I could say, well, I want to set the first and the second row. But that's not quite what I want to do. What I want to do is I want to generate an array that represents all the random flips, and then actually do that flipping. And this isn't quite what I want. Instead, what I could use is numpy.put. I can create an array of zeros, 4 by 4, select the first and the second value in this flattened array, and put a 1 into those 2 places. Now you're beginning to see how this can be built up. Because what I'll do is I'll create a random array with values from 0 to 4. I'll take those and I'll scale them up so that those values now represent offsets in my flattened array. And so here you can see these are offsets in my flattened array. And then what I'll do is I'll put 1s at all those offsets. What you can think is I can perform all my bit flipping at once by selecting all of the bits in the flattened array where there'll be flips, and I can perform all the bit flipping at once using a single call to numpy.put. So here's what this looks like for the entire population. Here's the bits that I chose for each of my populations. Here are the indices for where the bit flips are going to occur. Here's the scaling of those to flattened indices, because even though I look at this as a 2-dimensional structure, in NumPy, this is just a block of memory, so these are the actual memory offsets. Or rather, here are the actual memory offsets. These are the actual places where I'm going to do the bit flipping. And then what I can do is I can put a 1. So here you can see I represent the entire flipping of all the bits for the entire population all at once. And I can repeat that a certain number of times. And one really neat thing that I can do is if I represent the flips. So here you can see here are all the bit flips I'm going to do for my population. I can actually do all the flips by doing a single XOR operation. And so I end up with some code that looks like this. This represents the entire process of breeding these. What I do is I create my random population. I select my mates. I figure out which are the parents on one side, which are the parents on the other side. I perform my crossover like this. I create a mask and then create offsets from those masks. I flatten the array to create those offsets, and then I put a 1 to represent all the bit flipping. That represents one stage of bit flipping. And then I create the probabilities. And what I can do that's very interesting is I can perform multiple bit flipping simultaneously. Previously, for a chromosome of size 5, I could flip it. I would allow it to do it up to 5 bit flips. I can actually perform all of those simultaneously by taking each of the arrays that I had for those bit flips and XORing them together. Because you can think, if I said flip here and I said flip again, that's the same thing as not doing a flip at all. So I can remove even one more layer of looping by performing, in aggregate, all of the bit flips all at once with a single matrix operation, or single NumPy operation. So with that, I want to show you all the code put together because I'm running out of time. Here you can see I have number of steps, my population size, my number of couples that are going to be chosen, the number of mutations that they might have, my mutation rate, and here I have my simulation. I will still use a pure Python structure because the different matrices, the different higher dimensional matrices representing each of my simulations for the size of the chromosomes are not same sized. I can't put them into one big NumPy array. So I still use a Python dictionary keyed on the length of the chromosome, where each of the elements of that chromosome is a list, where each of those lists represent one step in the evolution of this population. And then what I do is I compute the mask for where the bit flips will occur. I take my last population. I choose the mating pairs. I compute the crossover indices. I perform all of the bit flips simultaneously at once. I compute where the bit flips would be. Then I generate the probabilities for all the bit flips. And then I perform in one step here at the bottom the crossover and the bit flipping simultaneously using a single expression, which itself internally implements all the looping that I had to do externally in Python. And what you can see is it takes 1 second. And if I can scroll down, the results are right here. Those are results. And those are the results that I expect. I see convergence towards perfect fitness. And you can see this took 1 second to run. My previous example took 2 seconds to run, but one thing I didn't highlight for you is this population size is 10 times as big. So this is actually an order of magnitude faster than my last simulation. So that's NumPy approach. I'm pretty much out of time, but I wanted to show you a design exercise for how you take a problem, how you'd solve it in pure Python, and then how you'd flip on your head your thinking in order to design this in a NumPy approach. I hope that you appreciated that. It's been my pleasure speaking at this event. Thank you so much.